Greetings. In this video, we're going to learn some interesting properties of graphs. This is actually very interesting, very useful, not very hard to understand either, so it should be a lot of fun. Notice I've got two graphs over here. One is an undirected graph, one is a directed graph. The theory that we're going to develop here actually applies to both of these with a little bit of a difference. But again, notice I've got exactly the same set of vertices. I do have edges between the same points over here, except over here they are directed and over here they are undirected. And what I want to introduce here, there are a couple of things here. We want to talk about what is the degree of a node. And then we also want to talk about what is the degree of a graph. These are very related. And I'm going to start over here looking at the undirected graph. And basically, we define the degree as just the number of edges coming into it or adjacent to it. So over here, for example, if I look at this vertex numbered 1, we can see that there are 1, 2, 3 edges coming in. So I would say the degree of 1 is equal to 3. And likewise, if I come along here, I would get that the degree of 2 is equal to, well, I see 1, 2, 3, so that's equal to 3. And I would see that the degree of 3 is equal to 1, 2, 3. And the degree of 4 is equal to 1, 2, 3. And the degree of 5 is equal to 2, right there. Okay? And we talk about the degree of a graph. So if this is my G over here, we say that the degree of G is equal to the summation of the degree of all of the vertices in there for VI contained in G. So in this case over here, it would just be 3 plus 3 plus 3 plus 3 plus 2, 3, 6, 9, 12, 14. So over here we would say that we have the individual degrees of the individual nodes, and then we have the total degree of the graph. Now, I think we can keep this up here. What happens when we talk about the undirected graph, or I'm sorry, the directed graph, that was it's so easy to correct the mistakes when you're working with high-tech tools, right? The directed graph, the notion gets just a little bit more complicated. When we look at a particular node, we can ask the question, how many edges are coming in, how many edges are going out? So for example, in this example here, we can talk about what we call the in degree. And then we can also talk about what's called the out degree. And for example, if I come over here, I'm just going to say in D of 1. Well, how many are coming in? There's just 1. And the in degree of 2 would equal, well, how many are going into 2? And that's just 1. And then the in degree of 3 into 3, I see 2 going into 3. And the in degree of 4, how many are going into 4? I see 2. And the in degree of 5, I don't see any going into 5, so that's equal to 0. And then I can come over here and I can do the out degree of 1, and I can see that there's 1 leaving 1. And the out degree of 2 is 1, 2. And the out degree of 3, how many are leaving 3? Well, there's 1. And the out degree of 4, doesn't look like any are leaving 4, so that's equal to 0. And the out degree of 5 looks like it's equal to 2. And there's something to notice over here, that if I come over and I add these up, 2, 4, 5, 6, and I come over here and I add these up, 2, 4, 5, 6, we would get that the in degree of the graph is equal to 6, and we would get that the out degree of the graph is equal to 6. And I think you should all be convinced we can make this a theorem. Okay, for a directed graph G, okay, you're going to get that the in degree of G is equal to the out degree of G. That shouldn't surprise you, because every time I draw a directed arc like that, okay, well, for every point, every time it's leaving a point, it's going into a point. So this result over here should not be surprising. But here's the result that may be a little bit surprising. I want to go back. First, we'll talk about the undirected graph. So over here, let me move things around. Okay, we saw over here that in our undirected graph, the total degree of the graph was 14. Well, first of all, let's think about something. Here's a point, and here's a point. Every time I put in an edge, okay, you can see that what I'm doing is I am adding, okay, each edge adds 2 to the degree of the graph. Okay, so in fact, and remember, for the moment now, we're talking about undirected graphs. If I have G is equal to, remember we said G can be recognized as being vertices and edges, okay? Where these were sets, okay, we can say that the degree of G is equal to 2 times the number of edges. Okay, and remember what happens when I take a set and I put these absolute value signs around it. This is the number of edges. Okay, this is a very useful result, and we're going to be using this a little bit later. Now, for directed graphs, okay, what we know about directed graphs is, remember, we know that in degree is equal to the out degree Okay, so the thing that we know here is we do know that the in degree of G plus the out degree of G is an even number. And why do we know it's an even number? Because these two numbers here are the same. If these are both even, adding them is even. If these are both odd, then the result is even. So this is a very, very interesting property to know. It's very useful. We can get some interesting corollaries out of this. For example, corollary in an undirected graph the number of vertices with odd degree must be, and before I write the answer in there, can you guess what it could be? Well, the answer is there must be an even number of them. If there were an odd number of them, then when we add them all up, we're going to get an odd number. And then when we would add all of the ones of even degree, we'd still get an odd number. But the total degree of a graph can't be odd. It has to be even. Okay? Let us consider an interesting application of this. I believe that all of you know Dr. Hashiana. And I know Dr. Hashiana, and Dr. Hashiana also knows me. So what I'm going to do is I'm going to draw Hashiana, and I'm going to draw a bill. And what I'm going to do is I'm going to indicate the fact that there's a line between us indicates that we know each other. Perhaps some of you know Mr. Matunga. And it turns out I also know Mr. Matunga. So I'm going to draw a line between myself and Mr. Matunga. Then I'm going to come over here and I am going to guess that you all know Dr. Muffetti. So what's going to go is I'm going to draw a line between myself and Dr. Muffetti. So here's an interesting point that I want to make here. The point is that I know these three people. And here's something that I'm sure that you all know. Dr. Muffetti knows Matunga, and Dr. Muffetti knows Hashiana. And it turns out that Hashiana also knows Matunga. So I want you to notice what we have here. Each one of these points here, Hashiana has 3 points coming out of him, Matunga has 3 points coming out of him, Muffetti has 3 points coming out of him, and Bill does. In fact, you should recognize this thing over here. This is the complete graph with 4 points. So that another way to draw this, if we wanted to, would be this way. Everybody knows everyone else, so everyone's connected. So notice the degree of this point is 3, the degree of this point is 3, the degree of this point is 3, and the degree of this point is 3. So 3 plus 3 plus 3 plus 3 equals 12. So notice that the degree of the total graph, and we could call this an acquaintance graph, is even and everything's fine. But now I have a question. Suppose there are 5 people in a room. Suppose there are 5 people in a room. is it possible that everyone knows exactly 3 other people? Well, let's think about that. So I've got 1, 2, 3, 4, 5. So let's see. If this person knows 3 people, that's 1. And then we know 1. And then we know 1. So this person's okay. So now we have to have this person know 3 people. Well, let's see if we can do it. Well, this person already knows 1. He's got to know 2 more. So we'll come over here and we'll draw that. And we'll draw that. Okay? So now I come over to this person. Well, this person already knows 2 people. He's got to know 1 other person. Well, I'm feeling bad for this person here, so why don't we have him know that person? So far things are looking okay. This person knows 3 people. This person knows 3 people. This person knows 3 people. Now this person knows 2. And at this point, watch, I can't draw a line between these 2 because then this person would know 4. So I'll come over here and I'll draw this one down here. Okay, so here's 3, 3, 3, 3, 2. But now, who can I draw this to? And the answer is, I can't draw it to anyone because then somebody would know 4 people. Well, I really didn't even need to go and draw this picture. Suppose that you did have a graph where every point, okay, you had a graph with 5 vertices on it, and you're claiming that the degree of each point on it is 3. Okay, but then that's saying that the degree of G would be equal to 3 plus 3 plus 3 plus 3 plus 3. That's, okay, this is for each one of the 5 people. That's equal to 15. But 15 is an odd number. Okay, and the answer is this is impossible. Okay, you can't have 5 people in a room. Is it possible that everyone knows exactly 3 other people? No, it's not possible. What about 6? So what about 6 people? Well, I don't know. Certainly, I could have 6 times 3 is equal to 18, and that's an even number. So we haven't proven that it's impossible. That doesn't mean that it's possible. What I need to do is to see if I can construct a graph like that. So let's come over here, and I'm going to go 1, 2, 3, 4, 5, 6. And watch what I'm going to do. If I come over here and I do this, and I make like a star, okay, in this subgraph, if you will, everybody knows 2 people, okay, amongst these 3. And now let's come over here and do this. And now amongst these 3 people, everyone knows 2 people. So now what I'm going to do is I'm going to do something like the following. I'm going to connect this one to this one. So now this person knows 3 people, and this person knows 3 people. Now I can't connect this one to that one because then this person would know 4, but I could do this. Come over here and draw that. And now this person knows 3 people, and this person knows 3 people. And then I'm going to come over here, and I'm going to draw this one right over here. Okay, and you can see now everybody, of these 6 people, everybody knows exactly 3 other people. So the conclusion is, yes, this is possible. Okay, Very simple theorem, very, very useful.